بله. به نام خدا، من خیر مقدم عرض میکنم خدمت همه حضار. خیلی خوشحالیم که در ششمین سری سمینارهای زمستانی دانشکده مهندسی کامپیوتر شریف در خدمتتون هستیم. اگر در حین ارائه سوالی داشتید در چت باکس مطرح کنید. پس از پایان ارائه یا در حینش در صورتی که امکان بود و وقتی مونده بود سوالاتتون رو با سخنران به اشتراک میگذاریم و در صورت صلاح دیده‌ایشون هم صداتون رو وصل میکنیم که سوالاتون رو شخصا مطرح کنید. چت در حالت خصوصی قرار داره و به دلیل کمبود وقت امکان جواب دادن به همه سوالا فراهم نیست. در پایان هم برای دریافت بازخورد شما فرم نظرسنجی آماده شده که لینکش داخل چت باکس قرار میگیره. پر کردن فرم زمان زیادی ازتون نخواهد گرفت. پیشاپیش بابت همراهیتون بسیار متشکرم. من پیش از شروع ارائه معرفی کوتاهی از دکتر نواب داشته باشم. ایشون استاد تمام و مدیر آزمایشگاه روش‌های پزشکی به کمک رایانه دانشگاه فنی مونیخ و دانشگاه جان هاپکینز هستند و عضو هیئت علمی این دانشگاهند. دکترای خودشون از دانشگاه اینریا و بورس تحصیلی پس از دکتراشون رو در آزمایشگاه رسانه MIT گرفتند. دریافت کننده جایزه مخترع سیمنز، جایزه اسمیت سوسایتی تکنولوژی و جایزه 10 سال تاثیرگذاری IEEE ایزمار هستند. عضو انجمن MCCIA و کمیته های ایزمار و ICPCAI هستند. نویسنده صدها مقاله با ارجاعات فراوان و مخترع 50 حق اختراع ثبت شده آمریکایی و بیش از 50 اختراع بین‌المللی هستند و در حوزه جراحی با کمک رایانه، رباتیک پزشکی و یادگیری ماشین فعالیت دارد. متاسفانه به دلیل محدود بودن زمان قادر به معرفی استاد به نحوی که خوب در خورشون هست نیستم. به عنوان عضو کوچیکی از تیم برگزاری مفتخرم که از پروفسور نواب دعوت کنم که ارائهشون رو درباره تاثیربرداری رباتیک و Augmented ریالیتی با ما اشتراک بذارن. دکتر بیکل از اختیار شماست.
خیلی متشکرم، خیلی ممنون. حقیقتش این اولین باره که من توی همچین برنامه شرکت میکنم توی ایران. حدود 12 سال پیش تاک توی دانشگاه تهران دادم، ولی از اون به بعد دیگه این موقعیت پیش نیومد. خیلی متشکرم که من دعوت کردین که بیام اینجا صحبت کنم. همونطوری که حدس میزنید من احتمالاً بیشتر تاک رو به انگلیسی خواهم داد و چون مثل همه استادای دنیا احتمالاً زیادی صحبت میکنم، اگه که 5 دقیقه قبل از اینکه وقت تموم بشه من بگید، من سعی میکنم که یه جوری تصریح کنم پرزنتیشنمو. ما یک نسبتاً لابراتوار بزرگی در مونیخ و 3 تا بیمارستانش داریم و همینطور یک شعبه‌ای توی جانز هاپکینز داریم و با بیمارستان بالگریست زوریخ کار میکنیم. یه سری تصویرهایی که از پیپرهای مختلف من گرفتم. این گروه ماست توی یک ریتریوی با یک اینوایتد اسپیکر که گرگ هاگر هست از جانز هاپکینز و اون گروه پایین گروه مونیخه، گروه بالا گروه جانز هاپکینز و کاری که من پرزنت میکنم کار این جوان هاست و کار بچه‌هایی که با ما بودن و حالا دیگه مووان کردن رفتن توی پوزیشن‌های مختلف. کلاً گروه ما I probably switch to English. So my objective personally is computer-assisted interventions. However, if you want to bring dramatically novel solution to computer-assisted interventions, you need in surgery you are punished by the weakest link. If you have a surgical solution, whether that the weakest link is in segmentation, in workflow analysis, in visualization, in robotic action, in robotic imaging, the surgeons will not accept your solution. So you're punished by the weakest link. Therefore, we need to have a large group and we need to cover different bases to have what I call, these 3 different approach to research, which is fundamental research, radical research, and translational research. Therefore, also our team is divided into mostly computer vision and machine learning are the base for us. That's where we have our fundamental mathematical and machine learning tools. But our objective, in fact, is medical imaging, medical data visualization, and in particular, my heart goes towards intraoperative computer-assisted interventions. Therefore, since I'm very much interested in bringing solutions to surgery, the key is really collaboration with surgeons. And so recently, Javad Fotoui, one of my lovely PhD students at Johns Hopkins, who defended his thesis, told that during the 4 or 5 years that he had worked with us, what we found is that we are actually optimizing. We optimize many functions, but the main function we are optimizing is the following function between surgeons and computer scientists or engineers, where we are actually trying to have them co-localized. That's why we are very often at our hospital labs. Then we are trying to spend a lot of time with them. And then the way we analyze and understand information in the two fields are very, very different. So we try to bring these two together. We bring to minimize this distance between surgical and clinical thinking and computational analysis and understanding. These are some pictures of some of our major collaborators. Now, something that I want to focus here, and it's a kind of basis of many of the work we do, is what is the difference between intraoperative imaging and analysis and diagnostic analysis and diagnostic imaging. So until about 20 years ago, until 2000, we had a lot of advancements in Röntgen since X-ray development of X-ray in 1895. We had a lot of progress in the diagnostic and operative imaging. And the main reason was the requirement of intraoperative imaging, dynamic imaging in surgery, are very different than imaging for diagnostics, whether it's computer tomography or PET or magnetic resonance imaging. The requirement of diagnostic is compared to intraoperative imaging is very easy. In case of diagnostic, the patient goes to a radiology department or a nuclear medicine department. The technicians position the patient in a regular position. Imaging can take between minutes for CT to 30 minutes, 40 minutes, or 20 minutes for SPECT or MR. And then the patient goes home, and then the radiologist log in on his PACS system and looks at the images. This is very, very different than intraoperative imaging, where you're doing a surgery, so you only want relevant information. You're not interested in looking at whole anatomy. You're really interested in relevant information. The imaging has to be patient and exactly processed, and even one step of the process is specific. It has to be fast, because for diagnostic imaging, speed is resolution, is a spatial and temporal resolution. For intraoperative imaging, speed is life. You really are under pressure of time because the patient is bleeding open. You need to be very fast. Then you're not sitting behind a computer and you're not looking at your images on your workstation. You have your bloody hand inside the patient. So it has to be super easy to use. It has to be flexible, because you're going to have many different surgeries, many different patients, many different objectives. But at the same time, it has to be reproducible, which is a big challenge. It has to be safe. and it has to be reliable, but at the same time cost effective. So all this made development and progress in intraoperative imaging until end of the last century very, very slow. By the end of the last century, we had X-ray, not much farther than X-ray of Röntgen. We had basic ultrasound, and that was not very much used. We had endoscopy, we had laparoscopy, but that was it. We could not have high-level imaging. Now, if you want to do intraoperative imaging and satisfy all these conditions, the only way you can do that is to do it robotically. And this is why we focus so much on robotic imaging. So we started in around 2005 to move from diagnostic imaging to define new kind of imaging for intraoperative imaging. So instead of doing SPECT, I hope some of you know what SPECT is. Instead of, but I can explain it later if you need it. Instead of doing SPECT, which was taking about 20 minutes after injection of radioactive material into the patient, we started to use a handheld detector and go around the area of interest, track that handheld detector with an external tracking system, and start to do for the first time, start to do intraoperative SPECT, which we called it freehand SPECT. And this got, CE certification in Europe, FDA approval, and started to be used on thousands of patients. And then, because I come from augmented reality and computer vision, we had a third camera included in the system, as you see up there. And there we were also doing augmented reality and virtual reality as user interfaces, without telling the surgeons that this was augmented or virtual reality. Then we brought it to laparoscopic surgery, where actually, again, we are tracking the laparoscopic gamma detector. And then as we were moving, we were trying to do a tomographic reconstruction of the activity. And what you see now is not the interesting part, that's the injection site of the radioactive material. What will be interesting is what's coming up, which after a set of reconstruction, you start to reconstruct the nodule. And that's where you are interested, because that's the nodule you want to take out. So then later we started to work with, intuitive surgical at Johns Hopkins. Our team there started to do what we call drop-in probe together with Netherlands, the group in Leiden. And the idea was that you would drop a gamma detector into the patient, and then you would take it with the robot, you would do acquisition inside the patient, and then you would be able to do intraoperative, minimally invasive robotic acquisition of 3D SPECT. This was the cover of IEEE TMI in 2016. But what makes me really happy is that in 2019, the group in Leiden, together with their surgeon partners, they brought it for the first time to real patients, and they actually did drop-in probe 3D SPECT imaging inside the patient. So they brought this technology all the way to use in surgery. Now, those were very interesting, but since we were computer scientists behind this system, we had logged in all the events. And we could see that even though if everything was certified, reproducibility of humans were not very high. Surgeons were not nuclear medicine experts. So, for the same nodule, if you had surgeons with different abilities or expertise, you would get different reconstruction. All of them were enough for the surgery, but as scientists, non-reproducibility, precise reproducibility bothers you. And this is something you can absolutely get with robotic imaging. And we started to mount the camera, which now could be heavier because the surgeon was not holding it, and start to do robotics. And then we found out that this is really much nicer because, instead of a very quick calibration, the robot could spend the night doing tens of thousands of acquisitions and do super calibration. Then it was very hard to tell a doctor, that there was so many becquerel of radioactivity injected at which time, and what is the half time half-life of that material. And therefore, since your surgery is, so many hours after the scanning, after the injection, how slow or how fast should you go to get the same reconstruction? But for a robot, this was much more or less straightforward. And therefore, we showed that the robotic could get much more reproducibility by adjusting the time and trajectory of the acquisition to the amount of radioactive injection. Then later we had the possibility also to, instead of, before we were telling the surgeons to go very smooth to do a reproducible acquisition, with a robot, we could actually go totally optimized. We could find, once we do one acquisition, the second acquisition has to give us the most, informative information. And that we did it based on our matrix of measurement. And therefore, we could actually do much faster, better reconstructions with a robot. Now, later, we started to see that in reality, they use also ultrasound to look at the anatomy, and then they look into nuclear to look at the activity, functionality, of physiology of the nodule. And now the idea was that the robot would actually work with the surgeon. The surgeon would do the ultrasound acquisition, and the robot would make sure that the SPECT imaging was always orthogonal to the plane of the ultrasound. This actually got the award of MICA in 2016 for intraoperative solutions. And basically, we showed that these two robots the robot can work with the human in a collaborative manner to optimize this acquisition. And also, we were using computer vision in that case to do the acquisition. And then in 2014, for the first time, we were able to do intraoperative SPECT CT by actually doing a cone beam CT acquisition, then having the two robots, which is the X-ray robot and the gamma robot, what we call kissing each other to make sure that they are in the same board coordinate system to co-calibrate themselves and make sure that the accuracy is in order of sub-millimeters or millimeter. And then based on the cone beam CT acquisition, the doctor would say, this is my area of interest. And then the robot would compute a trajectory to optimize the estimation of the radioactive measurements in that area. And then it would do an SPECT reconstruction. So that would mean in less than about 5 minutes, we would have an intraoperative functional and anatomical images ready for the use by the surgeon. Now we wanted to go to ultrasound. We wanted also not only the gamma to be robotic, but the ultrasound. But the ultrasound has this challenge that is touching the patient. And actually, the quality of the acquisition is very much depending on the force, on the contact, on the gel, on the way you take it. So this is much more intelligent or difficult than a system of extra CR, SPECT CT, which was based on gamma rays and had no touch to the patient. So the first thing from my point of view, one of the major contributions was the work of our students, Athanasios Karamalis, where we started based on random walk and physics of ultrasound to actually compute the probability that a sound wave from any point, any pixel on this image would reach one of the sensors up there. And on the right-hand side, what you see after the optimization is actually this probability. And that probability, we call it the confidence map, which means that here I have very high confidence on the X-ray. The gray is reduced confidence. And then I start to have low confidence. This is important because now if the robot is working and not a human, and somewhere the gel is not good, or pressure is not enough, or there is air inside the anatomy, then the system, an intelligent sonographer would move to have the best acoustic window. The robot has to do the same. But in order to do that, it has to fully understand what does it mean, a good acoustic window. Later, we did in IEEE Transactional Robotics and Automation, we showed that one can do now a servoing, ultrasound servoing, based on optimization of this confidence map. So to optimize that, the robot, if you move, the patient moves, the robot moves, to always keep the anatomy of interest with in the very good acoustic window. Then we started to say, can I be more ambitious that the surgeon or the doctor looks at the atlas of anatomy, not my patient's MR, and says, I want to measure this. For example, I measure the properties of the aorta. And then the robot, thanks to also computer vision, would be able to actually go and do automatic acquisition of the volume of ultrasound, does the compounding, and does a deformable registration to the atlas, and then measure what the doctor wanted to measure in terms of atlas on the actual patient. So we did that in over 50 volunteers, and it was really interesting. This is one of them. This is Oliver, one of our PhD students. And this was based on also an IRB and ethical approval at Johns Hopkins. So as you see, the system goes, the system measures now the acquisition of the ultrasound. This is done based on a rough registration with the RGBD camera. And then once the volume is acquired, then the volume is compounded, and then there is a deformable registration to the atlas. Then what the doctor wanted to measure on the patient is transferred now to the real person, and then this volume that you will see in a second is registered and the measurement is done. Now, since we work at the hospital, we have open days, and then the surgeons come and see, and the spine surgeons got super interested. So two lady surgeons that we have, Anna and Yumi, they got very excited, and they also got ethical approval to go to real patient. This is the first patient. So they tell us where and from where to start and when to finish. The robot automatically does a 3D volume acquisition of, in this case, the spine. Now, in this 3D acquisition, they can see the facet joint actually better than X-ray. Then what they do is that we show the 3D volume interventionally, and they actually define the facet joints on it. Then iRobot go to the same position on the patient, such that the image is the same image plane that they did in the 3D, and the injection attachment is exactly aligned with the direction that the doctor is defined. And then they started to inject. We did until now 20 injections on 5 patients by Anna and Yumi, all successful. We do an X-ray to verify the success of the procedure, and this was a big success. I always make the joke that the most famous surgeon was Mark Merkel, but Merkel came to visit our lab, and then she also played with the system, and then she put it on her Instagram, and Coco was super happy about that. So anyhow, this was, at this point now we came, and then we started to get very motivated. My question was, can I do automatically? This is one of the rare cases that I believe that an automatic system would perform better than a surgeon, an average surgeon. More reproducible, more precise. But then we definitely need machine learning, because we need to be intelligent, and many of the intelligence comes. Very simple things like, where to start, how to do the acquisition, to find my, things that you saw that the surgeons did. They defined the beginning and end. Then they defined the facet joints. These things, if I want to do it correctly and taking all the variability of the patient into account, I can only do it with machine learning. So we started a few years ago using machine learning. This is the work which was published in Robotic and Automation Letters, and of Maria, two of our roboticians. And the system grows and combines, pressure and force in terms of pressure, like a human which touches the vertebra, and the ultrasound, actually the level of vertebra. And once it comes to a vertebra of interest, it rotates and gets a very high precision ultrasound of that particular vertebra, and then runs the machine learning to actually detect the facet joint. And now we are working together with DLR in Germany to also do the going towards automatic injection. I personally believe this is one application where automatic system can work more precisely and more robustly, more reliably than humans. But this is not the case of most of our applications. Currently, this is one exception that would be the case. Now, still, there was one point that still in this application that you saw, we did it manually. We put it on the sacrum. Now, can the system find the sacrum? And we put the challenge and say, can I use only ultrasound to find the sacrum? And this was the work we did actually with one of the Sharif's PhDs who was 1 year with us as an exchange. Actually, he's on the 3rd year now, Farid and Hannes. And we use now reinforcement learning to learn how to automatically, that wherever you put the robot on the back of the patient, the system tries to use reinforcement learning to get actually to the sacrum. So then automatically, if this happens, then the system can do the rest. We are almost ready. We're very close to be ready for that. Now the whole system would be kind of automatic. But we are also, of course, at some point, we are also fuse it with other things like computer vision. But the problem with the computer vision, just for you to know, is that the patient usually is super covered because of sterility, and it's only a small area is visible. Then, of course, we are very much interested in vascular. And in here, we are doing an insertion of catheter. And the idea is that we do a servoing of the robot following the catheter and register it automatically to CT. Again, first we did that with imaging and optimization. I would say rather classical imaging, classical registration and optimization. It was working, it was very interesting. However, again, if you want to do it more reliability bring to the system, then we need to do it with machine learning. So we started also to do a large number of work on machine learning in this case. Let me see if it works. And I can show you the video. Yes. So now there are 3-4 students working on the machine learning in this case, where we try to automatically acquire the images, the robotic images, and also based on the force, we find the orthogonal view to the vasculature. The system compensates for patient motion, does at the all-time segmentation, all based on machine learning, and now more or less the system from A to Z can become automated. So this is how machine learning brings things into the game, which allows us to be fast, more reliable, more reproducible. However, if you want to go to surgery, it's more complicated than that. There is a complex surgical workflow that since 2006, we started to try to represent it automatically. And now here, machine learning started to be a player very early. The idea is that you want to, digitally know which phase of surgery you are. So you have a digital representation, a statistical graph representing the surgery. You have people. Now we are trying to also represent them with a scene graph. This is our recent paper in ECCV and CVPR, not on surgery, but there is scene graph from computer vision. We are bringing it into the surgery room. And then we want to have mappings between which information is required by whom, at which moment, for what. And this would allow us to become more and more intelligent. So we started, this whole field of digital-based, machine learning-based surgical workflow analysis. At the beginning, it was based on dynamic time warping, then later it was hidden Markov models, then random forest, and of course, in the last years, we are focusing on machine learning. And in the last work we presented this October, actually, we used temporal convolutional networks and dilated residual layers to actually replace LSTM, and in this case, and try to use a sequence of videos of surgery, minimally invasive surgery, to automatically find in which phase of the surgery we are and what is the next step, what is the objective, which information we need. In the same MICAI, but this time the first work was in Munich, the second work is at Johns Hopkins. We started to also do very fast tracking of the tools in order to be able to do several things. The tool tracking in minimal invasive surgery is a key. First, for phase recognition, and here we use gated residual units to go very fast to do during the training, to be able to do very fast reconstruction or detection of and segmentation of the tools. And again, this is now the power of machine learning. But what is my interest, as you know, I'm coming from augmented reality, is that if I have a registration of this data with the nodules coming from CT, if I just superimpose it, it would be floating. So what I need is actually this tracking in order to allow us to do a good visualization. Is it the time where I have 5 minutes left, or am I already out of time? Okay, if I don't receive a feedback, I continue. Maybe some of you know my hearted reality. So we brought the first set of augmented reality used in surgery. This was sentinel lymph node surgery. And then based on an invention that we had in 1998 to do X-ray and optics. This is what we call camera augmented mobile CR, whereby construction, vision, and are co-registered. This went to surgeries in 2010, 40 surgeries of trauma. So you position the patient using optics. By constructions, they are co-registered, and therefore the surgeon can start doing the surgery, seeing his hand or her hand, but not getting any radiation because the X-ray is stopped. Now, again, this was very intelligent, and this was the very first time in the world where X-ray and optics were co-registered in 1999, but used on patients in 2010. However, we need machine learning to do good visualization. What do I mean? If I look what we had, which was amazing, was what you see in the left-hand side. But what you see in the left-hand side is just superimposition of X-ray and optics. At the same time that this is an amazing augmented reality image, you're messing up with the optic as well as X-ray. What you see on the right-hand side is that the machine learning on the same two sequences decides for every pixel to which object does it belong to. And based on this classification, you do a very intelligent fusion, which we call it relevance-based fusion. And now suddenly, the same two images on the left-hand side are integrated in the right-hand side such that they are optimized for the surgery. And without machine learning, you cannot do that. So this is really the next step. For me, many people talk about augmented reality, but they only do data fusion and superimposition. That's not augmented reality. Augmented reality should not prevent us from seeing some very important information. And what we see here, based on combination of machine learning and that, is very intelligent imaging. The last part I want to talk about is computer vision combined with X-ray again in real time for intraoperative imaging. Here we do chromium reconstruction, but thanks to RGBD imaging, we can have both the surface of the patient and the internal. And then when the doctor brings his hand or her hand, then we can see all of the data without any X-ray exposure and without any navigation system. Now everything is in the same board. You have the optical reconstruction from computer vision, you have the tomographic reconstruction from medical imaging, and you have the dynamic imaging and segmentation thanks to machine learning and computer vision. And now you can do intraoperative planning, you can go further. But of course, this was also used by a company on their products to do it directly and to use it within the spine surgery. I go faster over that. But in augmented reality, we love to use head-mounted displays. And now the idea was, can I do that? Can I put an HMD on top of the surgeon and let him see what he cannot see? And the funny thing is that what we did is that we attached a HoloLens also to the X-ray system. And the reason we did that is basically we want everyone to be in one world coordinate system. And the HoloLens 3D or 2D cameras have the capability of acting as the slave, master and a slave. And the idea is that the camera attached to the C-arm plays as the role of the master for the camera here. So they are both using, in computer vision, what we call a SLAM. We are not using any markers. They use the environment to do the reconstruction or the tracking. And the one attached to the C-arm is fully co-registered with the X-ray system once per in factory. And now when he uses it, it uses things on the ceiling. It transfers the same natural markers coordinate system to the HMD of the surgeon. And therefore we came to this interactive flying Frustum concept, which actually allows the physics to come into the direct view of the surgeon, which means that as soon as the X-ray is taken, the physical source and detector is visualized, and then you know that this is the geometry, this is the projection geometry. So the surgeon can actually take the X-rays and bring them back to the patient. So you completely understand now the physics, and then you can manipulate it and you can bring it into the surgery. So we did that about 2 years ago. And then the idea was right away, can we actually change the workflow? Can we totally change the workflow of the surgery? And it took us some very nice collaboration with Alex Johnson and Dr. Osgood at Johns Hopkins. They found tens of applications. This is after the surgery, they want to review what was happening, what the surgeon did. And now they're seeing all the X-rays which are taken, which to your surprise for pelvis, they're in average about 120 X-rays. And now we want to do also computer vision reconstruction and then having a full experience of a surgery, including X-ray and optics, all in one coordinate system for teaching and training. You can also tell the assistant to move back to a position that you take an X-ray in the middle of the surgery. And now this alignment can be done manually. And even if your X-ray is not robotized, you can push it to the same position. You can also do intraoperative planning by telling, okay, where do I put my device, and then see it directly in the X-rays. So these are really interesting because now your X-ray, your optics, your hand, your tool, all are in the same virtual world coordinate system. You can also say, what happens if I put my prothesis inside, and you can see exactly what the X-ray should show in that case. Now, one of the things that our surgeon, Dr. Rosted, loves is that he can actually look at the X-ray and say, I want to enter my drill from here to test it on 2 images. It defines those blue and pink spheres. But when he looks at the patient, now he sees those in 3D on the patient. So those points that he decided based on anatomy of the X-ray, now he can see it in the patient. He can then take a virtual drill and say, okay, this is how I want to drill it. These are all A to Z intraoperative. Now he can take actually the drill itself and then try to do the alignment. Recently, we also had worked with ETH on computer vision, detection of the drill and the pose based on a 3D cloud of points and machine learning, of course. And now suddenly you can bring everything into one word. So A to Z, novel workflow, and then he's starting to align and to do his drilling and into the patient. So this is really A to Z augmented reality. So this was actually, after 2 years, I think one of the first papers in augmented reality, which was published, accepted as IEEE transactional medical imaging. And then we showed all these different workflows that you can do with augmented reality from A to Z inside operating room. There was one part that I had to take out because I could not transmit with you the sound. But you may look at our awarded papers at ISMAR 2017 and also MICA 2017. What we started is that we started to say augmented reality is not only vision, it's also acoustic. And if I augment everything with the vision, then I have limited capability of data fusion. So we started to put music, but the problem is that music has to be very pleasant because they are doing surgery 8 to 10 hours per day. If you start telling them beep, 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 beep for 10 days, 10 hours per day, they would just turn it off. So what we did in those works, we used a selection of the doctors of, in that case, was classical music, but it can be jazz, it can be Persian music. We also use actually Greek music. And then based on the signals, for example, based on a distance, based on the tissue that we are touching, you change the music. So unconsciously or consciously, they know in which they get the status. So this segmentation becomes visual, but also acoustic and hopefully haptic, which is very difficult. I thank you for your attention. This was just a panacea of the work we do. This is also, I finish on this. This is what we put in museums for people to learn their anatomy. They can also use their CT and MR. They can use, with one hand, you're controlling the details. With the other hand, you're comparing the superposition. More complicated system of that was used in the medical school. Now it's used on 900 patients in the medical school at TU and about 300 at Johns Hopkins, used for teaching anatomy, but more complex than that. This was for public and patients, not patients actually, publics and schools and etc. I hope you enjoyed the talks. You can see a lot of information on our website. You can also, for the augmented reality part, you can go to medicalaugmentedreality.org. If you have any questions about anything I talked about, I did not talk about a lot of things we do, but I took a selected part of it. If you have any questions, please go ahead and ask. Thank you for your time.
ممنون برای ارائه خیلی جالبتون. خسته نباشین، دستتون در نکنم. سوال پرسیدن در حین ارائه، من از آخر شروع میکنم سوالا رو پرسیدن. یکی از حضار پرسیده بودن که خب ربات مال کمپانی کوکا هستن یا جایگزین و رقیبی هم براشون وجود داره؟
خیلی ربات مختلف هستن. کوکا actually was the first one who was safe, and they had also a certification which was important for us. ولی در حقیقت برای آتلاسان درست نشده بود. الان خیلی از کمپانی‌ها دارن ربات درست میکنن برای آلتراساوند. برای آلتراساوند من لازم ندارم یه همچین ربات هیوجی داشته باشم که کوکا باشه. کوکا برای ریسرچ لبی مثل ما که هدفش ایمیجینگ و کنترل و ماشین لرنینگ بود اپتیمال بود، ولی اگه کسی بخواد بره توی پروداکت، رباتی که خواهد ساخت خیلی کوچیک‌تر، خیلی probably attached to the bed. ما الان داریم با کمپانی به اسم فرانکا کار میکنیم، فرانکا توی مونیخ، توی برلین، که رباتش خیلی کوچیک‌تر، خیلی ارزان‌تره. کمپانی‌های فرانسوی و چینی هستن که ربات‌های خیلی کوچیک درست میکنن. It doesn't need to be KUKA. It has to be hopefully smaller and fitted to the procedure. ولی ما کوکا استفاده کردیم برای اینکه برامون راحت‌تر بود استفادهش و نمی‌خواستیم ربات خودمون رو دیولپ کنیم because we are not robot developers, we are imaging and visualization guys. ولی من حدسم اینه که چند سال آینده خیلی ربات‌های آلتراساوند میاد بیرون.
دستتون درد نکنه. یکی از حضارم پرسیده که نصیحتی راجع به این که دانشجوها چی میخوان این فیلد رو شروع کنن، از کجا شروع کنن دارید؟
حقیقتش نصیحت خیلی دارم. وقت کمه. من امروز بعدم توی قبول کردم که توی پنل راجع به ریسرچ صحبت کنیم ساعت 7:30 شب ایران، 5 بعد از ظهر. من بیشتر راجعش صحبت میکنم، ولی من یعنی پیشنهادم اینه این توی این فیلد اونطوری که به شما گفتم 3 تا بخش وجود داره: Fundamental Research, Translational Research, Radical Research. بستگی به کاراکتر شخصی شما یکی از این 3 تا رو باید از اول بفهمید. وقتی آخر بچلرتون هست، لیسانس یا لیسانستون هست، بفهمید که شما کدومش هستید. به نظر من هیچ کدومش از اون یکی برتر نیست. تو اکادمیا یه جورایی ما همیشه فکر میکنیم که fundamental is the most important. That's not true. این حقیقتش unfortunately believe شده که هست. نه، اگه شما میخواین pure physics یا pure mathematics بخونین، آره fundamental is the crucial one. بر همین تو اکادمیا چون هدفمون پروفسور درست کردن همچنین رو میگیم. باید به نظر من اول از همه بفهمید که شما هدفتون چیه. آیا شما interested هستین به radical solution؟ برای radical solution you have to be creative. You have to think outside the box. برای فاندامنتال شما باید متماتیکالی و کامپیوتر وایس خیلی قوی باشین. برای ترنسلیشنال شما باید کامیونیکیشن و مدلینگتون عالی باشه. شما باید اینتردیسیپلینری مدلینگ رو بفهمید که چطوری یه سرجری رو نگاه کنید و بعد اونو مدلش کنید توی کامپیوتیشن. اکسایتینگ. اولین کاری که باید بکنید ببینید که شما کدومش شما رو اکسایتد میکنه. آیا شما اکسایتد میشید وقتی که میدن که کدومش برای شما راحت تره؟ توی ایران همیشه به نظر من فاندامنتال راحت تره چون فقط یه کامپیوتر میخواد. ولی الان ماشین لرنینگ فور د کیس الان خیلی توی سالهای اخیر 5 سال اخیر چون همه شروع کردن ماشین لرنینگ یاد بگیرن توی فیلدهای دیگه غیر از خود ماشین لرنینگ الان شده یه جورایی همه فکر میکنن که فقط باید ماشین لرنینگ یاد بگیرن، ولی به نظر من تا 1-2 سال دیگه سچوریتد میشه ماشین لرنینگ. انجینیر ماشین لرنینگ همه جا پر میشن. اون موقع کسی جالب میشه که یه مسئله رو چه روباتیک، چه فیزیک، چه بیولوژی، چه کیمستری اونو کامل میتونه مدل کنه با ماشین لرنینگ. نه کسی که میتونه ماشین لرنینگ رو بفهمه. ما نمبر آدمایی که ماشین لرنینگ دیولپ میکنن خیلی بالا خواهد بود و سچوریت به زودی میشه، ولی این باعث نمیشه که همه فیلدهای دیگه برن کنار فقط بشه ماشین لرنینگ. برای همین نظر من شما بفهمید که شما تو چی قوی هستین و چی شما رو اکسایتد میکنه و بعد برین طرفش. multidisciplinary, you always have to do that. امیدوارم که جوابم مفید بوده باشه.
بعد جوابتون خیلی کامل بود، دستتون درد نکنه. یکی دیگه از بچه‌ها راجع به خود ارائه سوال داشتن، من اینو بپرسم. فقط ما بعد از ارائه ها یه کانال دیسکورد داریم که حضار میتونن برن و مباحثه داشته باشن. میخواستم ببینم آیا علاقه ای دارید که شما هم وارد شین و بچه‌ها بتونن سوالای خارج از ارائه ازتون بپرسن یا فرصت نمی‌کنید؟
من میتونم برای حدود 20 دقیقه تا نیم ساعت برم اونجا، بعدش دیگه باید بیام چون بعد دوباره میام برای ایونت بعدی، ولی میتونم برم توی دیسکورد. به من یه اکانت همکار شما دادن به اسم نصیر نواب. تا حالا با دیسکورد کار نکردم، بنابراین I don't know if I can go through it. I know how to register now, so I can go to Discord and see whether we can discuss, but this will be my first experience with Discord.
ممنون. پس من سوالی که راجع به وبینار هست رو میگم که بقیهش برم. یکی از دوستان پرسیدن که خطای این سیستما به چه شکلی هست و امن بودنش رو چطوری تامین میکنید تا خطر نداشته باشن این سیستم؟
این سوال خیلی جالبیه. نگاه کنید، این مسئله امنیت نیست، مسئله ریسپانسیبیلیتیه بیشتر، چون که مسئله شما وقتی خودتون به یه سرجن میسپارید اونقدر امن نیستید. یعنی مسئله اینه که ما احتمال اشتباه سیستم Artificial Intelligence روباتیک ما باید این اوریج بهتر از آدم باشه. To be honest, that's not very difficult. چون که ما خیلی هم سورپرایز میشیم برای وقتی به کامپلکسیتی مریض داره. ولی میدونین مشکل اینه یه جراح چرا خوبه؟ چون اون جراح احتمالاً کلی یاد گرفته و بعد 200 تا جراحی کرده یا هزاران جراحی کرده و هر چقدر بیشتر جراحی بکنه اکسپریانسش بیشتر میشه، احتمالاً بهتر یاد میگیره. سیستم‌های کامپیوتری در آینده اینا اگه که مدلینگشون درست باشه و اکسسشون درست باشه، اینا میتونن 10,000 100,000 کیس رو داشته باشن. الان نداریم ما هنوز توی سرجری، توی دیاگنوستیک و اینا داریم ولی توی سرجری متاسفانه این دیتا وجود نداره. بنابراین خطرش به نظر من در at some point it will not be amazing. ولی الان سیستمایی که ما الان داریم کار میکنیم مثل داروهای چیزه، یعنی اول ما روی فانتوم انجام میدیم، بعد روی کاداور انجام میدیم، بعد روی انیمال، بعد که اونجا دیگه واقعا باید اتیکال اپرووال داشته باشه، من نشون بدیم که انیمال داریم ابیوز نمی‌کنیم و ماکسیمم استفاده رو می‌کنیم روی اون رو باید تو آلمان حداقل ما نشون بدیم. بعد میریم توی ثابت می‌کنیم که ما سیفیم، بعد با سوپرویژن جراح توی اتاق جراحی میریم روی هیومن with the backup solution که سر جراح اون بالاش وایساده. مثل اولین سیستم‌های داوینچی جراح‌ها بالا سرش بودن، آماده بودن که اگه چیزی اشتباه هست شروع به تک کنترل بکنن و بعد که این روتین ثابت شد بعد از یک سری تست‌های دوره اول، دوره دوم، دوره سوم که پرسنتیج خطر کمتر از چیزه و کمتر از جراح‌های اوریجه یا بهترین جراح از خب امیدواریم، بعد کم کم میاد توی پرکتیس. ولی it takes time و مسئله اصلی و دیفیکالتی ریسپانسیبیلیتیه که اگه ربات یک کار اشتباهی کرد این اشتباه رو کی مسئولشه. نکنید یه چیز خیلی جالب براتون بگم اینه که وقتی یه دکتر رو یه جراحی اشتباهی میکنه، مثلا تو جانز هاپکینز ما خیلی راجعش صحبت کردیم و بر اساس علیهش شکایت میشه، اگه اون جراح تمام اینفورمیشنی که داشته بوده استفاده کرده باشه ولی تصمیمش غلط باشه، هیچ اشکالی نداره، این کار غلطی نکرده، یک اشتباه کرده که تصمیم، یعنی بیسد آن اینفورمیشن که داشته اشتباه، یه تصمیم غلط گرفته و ای که همه ما میکنیم. ولی وقتی مجازات میشه که مثلا به یه سری فایل‌های مریض نگاه نکرده باشه یا شب قبلش پارتی داشته باشه، سر حال نباشه، وقتی میاد حالش بد باشه، بنابراین اشتباه بکنه. ولی اگه اشتباه جاجمنت بکنه بر اساس دیتا، اون پانیشمنت نداره، چون ما هیچ کدوم خدا نیستیم، ما هیچ کدوممون آدمایی نیستیم که هیچ اشکالی نداریم بگیریم. اون تصمیم تو میتونی اشتباه بگیری اگه اون اشتباه به خاطر این نباشه که تو آماده نبودی یا کار غلطی کردی یا یعنی یه چیزی رو که باید نگاه میکردی. حالا این کیس ها تو روباتیک و آرتفیشال اینتلیجنس کمتر پیش میاد، چون سیستم نگاه میکنه به یه چیزی که تست شده، به تمام دیتا نگاه میکنه، سیستماتیکه دیگه. امکان نداره که بلاد پرشر رو نگاه نکنه. اگه تو سیستم باید به بلاد پرشر نگاه کنه، باید به این نگاه کنه، باید به اون نگاه کنه، یه سیستم اتوماتیک نگاه میکنه. این که آیا امکان داره که تصمیم اشتباه بگیره؟ 100%. میگه دکترها تصمیم اشتباه نمیگیرن، اونا هم میگیرن. بنابراین ما باید آماده باشیم از دو طرف، یعنی هم خیلی حساس باشیم. مشکل ترین مسئله که من همیشه روش اشکال دارم اتیکالی اینه که سیستمایی که فقط هدفشون پول در آوردن باشه، اگه سیستم هدفش پروفیت باشه، خطر همیشه اونجا پیدا میشه که سیستم try to optimize money not optimize the outcome. اون موقع خطرناکه و اتیکالی مسئله ایجاد پیدا میکنه که اونا دیگه بعد میاد به مسئله رگولیشن.
دستتون درد نکنه. من بازم ازتون تشکر میکنم که وقت معلوماتتون در اختیارم قرار دادیم. از شرکت کنندم تشکر میکنم برای شرکت در سمینار. لینک نظرسنجی و لینک دیسکورد، کانال دیسکورد رو گذاشتم. بحثای خارج از ارائه داشتین، سوالاتی که از دکتر داشتین رو لطفاً ببرین توی دیسکورد، لطف میکنم دکتر میام و اونجا
یه کامنت فقط اگه امکان داره من یه کامنت بدم، چون برای اونایی که امروز نمیان توی بحث ریسرچ، من خیلی درخواست میگیرم از دانشجوهای ایرانی که بیان پیش ما. یه چند تا بچه‌ها سالهای قبل اومدن و اینترنشیپ داشتن، ساکسسفول بودن، بعد رفتن یکشون پیش جف هنتن، بچه‌ها یکشون رفته ETH، بچه‌های شریف یا بچه‌های تهران یا بچه‌های جای دیگه از ایران. تنها چیزی که میخوام به بچه‌ها بگم که اینو بدونن اینه که میگن الان یه موقعیت پیش اومد که تو ایران هم شما میتونید خیلی اکتیو باشید و وقتی میاین آپدیت باشید. این خیلی 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 مهمه که از همون ایران خیلی اکتیو باشین و کامیونیکیت کنید، شروع کنید روی پروژه ها کار کردن و همیشه یه نگاهی به چیزایی که انجام میشه رو خودتون داشته باشین، چون الان هی بیشتر داره کامپتیتیو میشه که آدم توی فیلد وارد شه، ولی اکسس خیلی زیاده. حالا امشب راجبش بحث میکنیم. بازم ممنون از این اپورتونیتی. خب من الان برم بیرون و برم توی دیسکورد.
بله اگر وارد بشین لطف میکنم بریم.
خیلی ممنون. خداحافظ شما. پس اگه من موفق شدم که برم توی دیسکورد، بعضی‌ها رو اونجا میبینم. خداحافظ.
باشه حتما. ممنون.